Today, I would like to talk to you about calculating product distributions for free radical chlorination. And I want to look at this molecule with you first. So let's take a look. This first position here, we can see is a tertiary position. Carbon connected to 3 other carbons. This top position here has 3 H's and another 3 H's that are equivalent and also that are primary. They're going to lead to one product. The end of the molecule has another primary position. That'll lead to our third product. And at this position, we have a secondary position with 2 H's. Now, if you remember from our class, we saw that there was a different reactivity at primary position versus a secondary versus a tertiary position. This is something that can be determined experimentally, and the ratio is roughly 1 to 4.5 to 5.5. So let's take a look at individually these 4 positions and see if we can calculate what the product ratio will be for this reaction. So our primary position here, if we take off one of those H's and put a chlorine, we're going to get this as our product. Now if we look here, we can see that there are 6 hydrogens in total that are equivalent. Taking any one of those hydrogens off and replacing with a chlorine will give us this molecule, which is 1-chloro-2-methyl-butane. Now, the way that we're going to figure out the product ratios, we're going to take the number of equivalent H's and multiply it by the reactivity factor up here. So because we're primary right here, it's going to be 6 H's times 1, because that's right, primary is 1. So it gives us a total of 6 here. So if we move over to the next position, if we take off this H, which is at the tertiary position, that gives us this, which is right 1, 2. That's 2-chloro-2-methylbutane. Now the relative reactivity at this position, because it's a tertiary position, is 5.5. And notice that there's only 1 H here. So to calculate the factor for this, it's the number of H's times reactivity. So it's 1 times 5.5, which is 5.5. Walking down the line here to this next position, our secondary position, if we take off one of those H's, we end up getting this as our product. And at our secondary position, the reactivity is 4.5. All right, with 2 H's, it's going to be equal then, therefore, to 2 times 4.5, which gives us a factor of 9. And if we continue down the line here, we can analyze this primary position. So here we have 3 H's that are equivalent. Removing any one of them will lead to this product, which is 1-chloro, right, 1,2,3-methyl-butane. And the reactivity, as we saw before for this, has a factor of 1. 3 H's in total, so 3 H's times 1 gives us 3. Now, if we put all that together, we get kind of a busy looking slide here, right? But this is just a summary of the last 4 positions that we kind of looked at, right? You get a total of 6 here for a contribution for this top position here, both of these positions, I should say, these 2 positions. And then down here, we have a factor of 5.5, and then a factor of 9 and 3. So here we have a way to calculate with these numbers, a method to calculate the product distribution. So let's see if we can figure out the percent of the 1-chloro-2-methylbutane. We'll have to go through and do some stuff first. So the first thing is to recognize that its contribution to the total kind of, number here is 6. If we come over and look at our next molecule, that's 2-chloro-2-methylbutane. It's this. Its contribution is 5.5, right, to our sum of the relative reactivities. Moving over here, we have 2-chloro-3-methylbutane. Its contribution sneaks over there, and it's 9. And then lastly, we have 1-chloro-3-methylbutane, and its contribution is 3. Now, if we add all those numbers up together, we get 23.5. So that if we weight all of these contributions by that total and multiply by 100, we're going to get a percentage. So down here below, we can see our contribution of 6 divided by 23.5 times 100% gives us 26%, right? You can see here, we'll take 5, that's the contribution from this, divided by 23.5, and you get 23%, and so on and so forth. It gives us 38% for our secondary positions product distribution, and then lastly we get 13% for the primary position at the other end of the molecule. And we add these things up and we get 100%. So I hope this helps you when you encounter questions in which you're asked to calculate product distributions.